Hello, my name is Kaori Sánchez. I am a PhD student in material science and engineering, and today I'm going to talk a little bit about an article we just published that involves the synthesis of gold nanoparticles in a deep eutectic solvent using polyvinylpyrrolidone as a stabilizing agent.
The synthesis of gold nanoparticles has been widely studied in aqueous media since their discovery by Michael Faraday. These structures are of interest due to their unique optical properties. However, their synthesis in an alternative media, like nonaqueous for example, has been scarcely studied. In this work, we used a deep eutectic solvent made of choline chloride urea as media for the synthesis of metallic colloids through a chemical reduction methodology using ascorbic acid. This deep eutectic solvent has proven to modify the size, morphology, and crystallinity of nanostructures, resulting from structure-directing properties and viscosity, as a consequence from the speciation of its components and their hydrogen bond network when in liquid state. Specifically, we evaluated the effect of three different molecular weights of polyvinylpyrrolidone in the morphology, size, and stability of gold nanoparticles synthesized in a nonaqueous media.
We started with a 0.5 millimolar gold precursor solution in this, with heating and stirring. Once the solution was homogeneous, 1 weight% of polyvinylpyrrolidone was added with vigorous stirring. Simultaneously, 5 milligrams of ascorbic acid were heated in this. Once the PVP was dissolved into the deep eutectic solvent, the ascorbic solution was added to the gold precursor and PVP1. This was left with heating and stirring for 24 hours until the solution coloration changed to pink.
These nanoparticles presented quasi-spherical morphologies and sizes as low as 18 nanometers for high molecular weights and a wider size distribution for the lowest one. The colloids prepared with 40K Dalton's PVP presented an interesting emission phenomenon due to luminescent gold clusters in the solution. The prepared colloid showed great stability to solar exposure, centrifugation, and temperature changes, showing no signs of agglomeration, in contrast to particles synthesized in water using the same methodology. Such stability allowed us to prepare an eutectogel containing the gold nanoparticle. The eutectogel was made possible by adding gelatin to the gold colloid at high temperature and cooling down the solution to promote gelation, and trapping of the gold nanoparticles and the deep eutectic solvent into the polymer network. These findings mark the beginning of potential ionotronic materials with plasmonic responses for greener, flexible electronics devices.